hard to please me, but your voice is really all I need. Was it time? How you let me back? Baby, feel my fire. No, I ain't felt it all. Was it time? How you let me back? Baby, feel my fire. No, I ain't felt it all. Was it time? How you let me back? Baby, feel my fire. No, I ain't felt it all. Was it time? How you let me back? Baby, feel my fire. No, I ain't felt it all. I hope you never forget me. Call me just to say you miss me. Things don't turn out like they should be. Talking to you feel like ecstasy. I'm scratching through the surface, holding on to win, but the road tells me to be at your service. I thought I just might return, feet to you feel me now. So you said that you know where to go when you hold me down. To live and run free, first you gotta be hit to the ground, down to your knees. Then you get out, head above the dirt. Then you run free, faster than you've ever been. Love that you knew, waiting for time. Used to can't make it. Right in a drink with all of your sea. Let go, and run free. To live and run free, first you gotta be hit to the ground, down to your knees. Then you get out, head above the dirt. Know your body like, know your body like, back forth, back forth, back forth, back forth. Know your body like, know your body like, back forth, back forth, back forth, back forth. Know your body like, know your body like, back forth, back forth, back forth, back forth. Know your body like, know your body like, back forth, back forth, back forth, back forth. Know your body like.
You need to start.
Love it. Just the way I wanted to start this off. Thanks, Javi. All right, welcome everyone to GitHub Universe 2020. Hope you enjoyed the rest of the conference and learned lots of new things about GitHub. Today, we're excited to introduce to you all on how to keep your Git mono repos manageable. My name is Sarah. I am joined today by Javi. We're both engineers for the professional services team at GitHub, and we help enterprises manage to migrate to and utilize the GitHub platform. There are a few things that we asked for you to have ready for today's workshop. Hopefully you were able to do those. That included a clone or a fork of a repository you'd like to reduce in size, the time it took to clone the repository, because we'll need that later, some installation of Git LFS, Git Sizer, Git Filter repo, and then also a clone or a copy of the workshop repository, as there's some tools in there as well. Today, we're covering 3 sections. Each section has a hands-on activity for you to test and explore in your own repositories between each of the sections. We're going to start today by going over history, which will dive into what makes up a commit, how those commits can be contributors to the bloat of a repository. We'll also be covering ways to prevent this repository bloat and how you can remediate it if you're already experiencing it. Now, most of us know or have a pretty good idea of how Git works. However, I wanted to take a quick refresher on what comprises a commit and how commits contribute to the history within a repository. Commit has 7 major pieces. The commit message is a short description of the changes that are being made and is saved at the time of the commit action with the change set. Commit message is comprised of 2 parts, the subject line, which is limited to 50 characters, and the pattern of this subject line usually completes the sentence, "This change set will." The body is not always utilized, but it can contain pertinent information around the change set, including some release notes information. The committer is the identity of the person or the account making the commit. This can be different from the person that suggests or makes the changes to the code base, but often is it the same person.
And then you pray that somebody will pay you for it.
Next is the commit date. This is set in coordinated universal time, and it is actually the date and time that the commit is made. Then we have the author. The author is the identity of the person who authored the changes. It can be different than the committer, but often is the same. The author date, similar to the commit date, is set in coordinated universal time, and it is the date and timestamp of when the changes were actually made or authored. The tree corresponds to the Unix directory entries. Those represent a particular state of a working directory at that point in time. It can contain 1 or more entries, and each entry contains the SHA-1 hash of a blob or a subtree. And lastly, we have a parent. A commit object may have multiple parents. 1 parent indicates an ordinary commit. More than 1 parent indicates a commit that is a merge between several lines of history. Initial commits have no parents. Now, please remember that last line, because it will become important later in the session that initial commits have no parents. So all of our examples today will be taken from the Linux kernel repository. It is an open source repository that you can go and explore on your own later. Each time there is a commit or a merge, it's associated with a hash, which is a unique hexadecimal number that is associated to that collection of changes. For this example, we're going to be following the SHA-1 hash beginning with EFD838, which is highlighted in the red box. Here we see the git log of that hash beginning with EFD838. It gives us the full commit hash, the author, which is Mike Christie, the author date, the committer, which is different, Michael Triskin, the commit date, the commit subject line, and then in this case, they also use the commit body, and then who approved or signed off on the commit, which is Mike Christie. Now, this is one single commit that has this information along with the other information that was included in the previous, which included the tree and the parents. However, that one set of changes or hash is only thousands of hashes in the history of this repository. In fact, in the Linux kernel repository, which is a good repository, you can see that at the time of our preparation, there were almost 1 million commits in the history. That's 967,460 sets of changes that have been made in this repository. Each set of changes could include multiple items. These all start to add up and pile on. However, just like burying a cat in peanuts, it can be fun, but it is not easy for us to free ourselves like a cat can do by jumping out of the peanuts. It can cause a repository to slow in cloning it to your local machine. So what type of changes or files can cause this pileup to get larger faster? A Git repository contains every version of every file, but for some file types, this is not practical. Multiple revisions of large files increase the clone and fetch times for other users of a repository. Examples of these are test data files, Excel or Word files that may be documentation for your application, images, videos, and other things that may be needed, but may not need to be stored in the same location. We've also seen binaries being stored in the repository. Those should be stored in a binary storage system or artifact management system. And then also something that shouldn't be in a repository that may be there for any particular reason or no reason at all, log files. Using Git LFS to manage some of these files from the beginning can prevent some of the bloat. Git LFS handles large files by storing references to the file in the repository, but not the actual file itself. To work around Git's architecture, Git LFS creates a pointer file which acts as a reference to the actual file, which is stored somewhere else. GitHub manages this pointer file in the repository. When you clone the repository down to your local machine, GitHub uses the pointer file as a map to go and find that large file for you. By doing this, it's not bloating your repository with multiple versions of an already large file inside the repository itself. You can also do some cleanup of files in your existing repository by moving large files into Git LFS. We do have documentation with steps on how to do this that we can provide you later on if you are interested. However, I do want you to be careful because Git LFS can break some automations and it cannot be used with GitHub pages. Another option for us is grafting. Grafting is taking a living piece of something and transplanting it somewhere else. In this case, we're going to take a living piece of your repository and transplant it into a new repository without all of the baggage of the past. There is also a way to connect your newly grafted repository locally to the history of the past so that you can have that history if you need it. We will be getting more into grafting later on. However, I wanted to highlight that grafting, along with Git LFS, binary artifact storage, dependency managers, and all the other tools available to us are all ways of managing your monorepos. I've gone through a few things in this section. One of them is pulling a log of your commit history and looking at a particular commit to see what those changes were like. We want you to kind of go through some of those on your own repository now. If you go to the activity 1 issue in the workshop repository, you'll find the commands that are ran on the Linux kernel. Please run those on some of the files in your repository and also your repository itself, and report back some of your findings in the issue comments. Be sure to obfuscate or remove any sensitive data or information because it is a public repo. Once you're done, we'll come back, and if we have time, we'll discuss some of the results. If you have questions, please feel free to reach out to us in the issue or in Slack. And we're going to give you 10 minutes at this time to do it. We're going to play some elevator music, some of that great music we were listening to at the beginning. And just let us know if you have any questions.
I'm scratching through the surface, holding on to the road tells me to be. I am service. Thought I just might return. Feel to now. So you said that you know where to go. But you're holding me down. To let run free. First you gotta be into the ground, down to your knees. Then you get out and above the dirt. Then you run free faster than you've ever been. Now that you knew, waiting for time. Used to can't make it. Right in a drink. All of this thing, let go, run free.
Just a little over halfway. Just a reminder, we've got a little over 4 minutes left.
You gotta be into the ground, down to your knees. Then you get out, head above the dirt. Then you run free faster than you've ever been. Run free. I hope you always accept me. Accept me just the way I be. Might be a little hard to please me, but your voice is really all I need. Wasn't time, baby, let me back. Baby, feel my fire. No, I ain't guilty, no, wasn't time, baby, let me back. Baby, feel my fire. No, I ain't guilty, no, wasn't time, baby, let me back. Baby, feel my fire. No, I ain't guilty, no, wasn't time, baby, let me back. Baby, feel my fire. No, I ain't guilty, no, I hope you never forget me. Call me just to say you miss me. Things don't turn out like they should be. Talking to you feel like ecstasy.
Couple more minutes. I know if you don't finish these activities will be there. You can always go back to them. Right, kind of rounding down. Well, right. So what were some of the things you learned? Did you find anything that surprised you? Anything that you feel like you can take away from just this quick peek into your repository or into your commits? I know some of you may still be working on them. Some of you are looking ahead, and that's great. But just try to keep some of these things in mind that you found when you did this quick peek under the covers. So now that you know a little bit about the history of your repository, I'm going to hand things over to Javi so he can go through how to analyze your repository to get more details around what's actually going on in it. Javi?
Thanks, Sarah, for the really nice introduction onto the Git history. So let's just have a look to the analysis. So you've talked about the history, but at the end, the whole thing of the history is that it's kind of like immutable. Of course, you can change it, but the history remains. So what you add in the history remains in the Git history, and that's good. But also you may find that it has some things that you need to realize when you are putting things into Git. So as a rule of thumb, we would say that reaching a history at 1 gigabyte is already quite a lot, and you may be in troubles. When we say you may be in troubles, is that it may impact your user experience when they are using Git in your repositories, and also it may impact your CI/CD tools and other things that you are doing with the history. So in general, it's good to think that if your history or your repository is getting the 1 gigabyte size, you should start thinking of doing something to clean it up and make sure that it's a little bit smaller. So when we say it may be a problem, what we are thinking, so actually the reasons why your history may become big can be two mainly. The first one is that your repository is actually big. It has a lot of history, like it happens, for example, with the Linux repository, or it may be that you are storing things that you shouldn't be storing in the head of your history. So maybe just a cleanup may fix some of your problems. And when we say that there may be some problems with your user experience, what we are meaning? Well, basically, your developers are actually waiting time just to clone the repository and even doing things with it. It is also stressing the machine where you are storing that code, because there are processes like the pack and upload processes that basically they are taking CPU time on your machine. And the bigger the history is and the bigger your repository is, the more CPU it will require, even to go to the biggest machines that you can even acquire from Amazon or other cloud providers. Also, your CI/CD clones may become slow just because you're cloning it. Of course, you can improve it just with doing a shallow clone just for the first commit that is done in the repository. But still, you may have a problem if you want to do the whole clone, and it will be slower. And finally, just working with these kind of repositories becomes harder and harder with the time passing. Just an example of this UX experience, we just tried to do a full clone of the Linux repository, and in a machine that actually has a good RAM and good CPU, and also a big network connection, it took around 11 minutes. So imagine 11 minutes multiplied for all the people that actually have to clone the Linux repository, as well as any other repository. It's a lot of time, and it's summing it up. Additionally, let's talk about the CPU part. So this is an example of a CPU graph for an instance of GitHub Enterprise that actually had many repositories over 1 gigabyte. Even one of those was over 5 gigabytes. And this actually is a really bad graph because it's reaching the 100% CPU multiple times. And this means that you may get some unicorns in your instance. So you should do something to remediate this. And actually, one of the things here is that this customer had the biggest instance that they could buy in the cloud that they were. So imagine how big the problem is, because they cannot scale up just by adding more CPU or more RAM. So let's just talk about how you can analyze your repositories so you understand them better and may act against those problems that they are causing the size of the repo. And for that, we have 5 tools that we want you to run in the next activity, and we'll just go over them to understand them and see what are the inputs that it can give you. So the first one is Git Sizer. It allows you to get metrics and understand the size of your repository and get a level of concern for each of the different elements that are adding space into your repo. Additional to that, we have the platform samples repository, where there are 3 different scripts that you can run in your repository, and each of them will give you some insights on how the repository is. The first one is about LFS, and basically it allows you to find files that by the extension should be in LFS, like for example, MP3 or MOV files. All these kind of files should be in LFS and not just directly into your repo. Git find dir's many files basically is a script that allows you to get components that should be on a dependency management system and not directly added to your repository as plain. And finally, on the platform samples, we have the find dir's unwanted, which we will give you some dir's opinionated that usually are committed but shouldn't be in your history. Like for example, build 10, x86, all these folders usually shouldn't be in your repository because they are compiled folders, and they at the end get generated when you are compiling your code. And finally, the last script is git filter repo. It gives you a lot of analysis for your repository with different files, and each of those, some of them are also related to the previous scripts, and some of them will be new, but it's good to just run in your repository and understand better how all the size is being summed up when you are using it. So talking first of Git Sizer, and we'll just run all these scripts into the Linux kernel so you understand better how it looks like. And actually, I'm gonna just give you a spoiler. The Linux kernel is actually a really good repo, even though it's big, and it's big because of its history. So in this case, we just run the Git Sizer, and we can see that in the number of blobs is on the millions number, and same for the trees. So if we analyze the space that is taken, let's just go to the next slide. And we see that this space is actually quite a lot. It's adding up with the whole time of the history up to 12.8 gigabytes just in trees. And remember, the trees is the diffs between the different modifications on your files during the different commits that you're adding. Blobs are the actual files, and it's adding up to the 77 gigabytes. And something that is interesting, and that's why I say you should run these scripts into your repository, but because it will give you some interesting insights. The interesting part here is the level of concern, and there we can see the different stars, and this is giving us what is the level of concern that this specific line has on your repository. And just looking at that, we can see some brackets with numbers, like at the bottom, it says maximum parents, and it says 66. That's actually really strange, right? That's not something that you're expected to find on your repository. So let's just go there, analyze, and see what exactly happened. And just at the end of this script, we can see these numbers with the brackets and the shafts that they have, and where these kind of events happened. We also have here some statistics, but they are not really relevant for the rest of the thing. So let's just see that 66 parents that happened on the Linux kernel. And there you go. We can do git show with the hash the SHA that we see there. And actually we see here a merge with the 66 parents. And guess what? You have the author. So you can just go and ask that person, hey, what happened here? And is there something that we can fix? Because actually this is kind of like a concern on our repository. Shall we fix it, or shall we just leave it there? And just to give you an example of how a normal commit looks like, you have an example below which says git show D55, and there you have a normal merge with 2 parents, which is like the normal merges that you will see in your repositories. Okay, so if we go to the second script, let's just run the git find LFS extensions. If you run this in your repository, the kind of statistics that you will get is the types of files that your repository is having, and they are ordered by extension. So if you look at this, actually it looks pretty well because you see that there is mainly text, and that's what we expect in a repository, just text as much as possible. if you see something like binaries, it's not as good. And if we analyze the rest of the lines to understand the output of this script, we will see the L share basically tells you the percentage of things that you should probably move to LFS. In this case, it's mainly text, not much that we can move into LFS. And then there is also the count, which tells you the amount of files that you should put into the LFS. And finally, the size that these files are summing it up all together. So it's also a good way to see which kind of extensions are taking space on your repo. And as an example, we have now a repository that is not so good as it happens with the Linux kernel. And here we see that we actually have some zip files, like gz is the extension, and it says binary. And if we look at the L share, it says, yes, move everything into LFS. We have only 2 files, and from those 2 files, we have 143, this line is in megabytes. So this is 143 megabytes that we will save in our history in the repository just by removing this file and moving it to LFS. And it also offers you some things that you can add into your Git attributes. So the movement to Git LFS is happening faster. Just a quick reminder, Git LFS also has a tool to migrate the whole history of that file in your repository into LFS, because if you move just the last file, it won't actually be removed from your history, because history adds up. And then if we run the next script, which is the git find dir's many files, basically it will tell you the amount of files that are in each of the folders. This is ordered from the maximum to the minimum. And usually the most interesting part is at the top of the script. So even just doing the head 9 with the -n and 20, you will see enough results that are interesting. And well, here we see that the drivers folder is actually the biggest one. In the Linux kernel again, that's fine, that's expected, because we are expecting to have a lot of files for the drivers, and probably they should be in the repository. They are just text files of headers of C, so it is what it is. But we can check other repositories like this one. And actually, if we just look into the first elements, well, it says no modules. If you're familiar with JavaScript, no modules is where you store your dependencies. So someone did something really weird with this repository, pushing their dependencies that he downloaded instead of putting them into gitignore. So this is the kind of information that you will get just by checking of the amount of files that you have in those folders. You may catch some interesting things. Let's go to the next script. And the next script is git find dirs and wanted. And this is an opinionated script that shows you all the folders that we consider that may be interesting, like x86, lib, tools. Those somewhat used to have files or folders that usually shouldn't be committed into Git. And they usually have even binaries that are compiled. So just have a look and make sure that you don't see something that catches your eye in this script. In this case, we run it in the Linux kernel. And again, some of those folders, usually in your repositories, might not be good. But here, tools, lib, arc, all of those are okay because it's a kernel. Let's just have a look to something that is not so good. And in this case, another repository has some scripts that may catch your eye, like scripts, utils, lab, you get. Ben, I am not saying that this necessarily shouldn't be in the repository, but hey, just have a look. If it's in the repository and it should be, just remove it. And finally, we have also scripts backup. You may find maybe some backups there. It's just something to have a look. And finally, the last script that we want you to run on the repository is the git filter repo. This will give you a lot of statistics. If you just run it, you will see that the analysis gets done, and you will find it in the .git/filter repo/analysis folder. So it's inside the repo when you run it. It may take a little bit more time than others, so just have a look. When you run this script into the repository, you will find the following files. The first one is blob, shs, and paths. And this will just give you all the different paths ordered by size that are in the repository. And not only the blobs and shas that are in the head, but in the whole repository. So that's interesting to have a look. Then directories, all sizes. This one with the next one, which is the directory deleted sizes, will give you each directory and the size it's taking in your repository. even for the deleted ones. That's the second folder. So why not just have a look? Let's see if there is any folder that was committed once, but then it got removed and you did never notice about it. So that's actually taking space on your repository. Same for the extensions, all sizes. It will get for each of the extensions, the size it's taking. And it's not only on the head, it's taking it for the whole repository. So just have a look. If you have a mob file that is actually taking a lot of space, probably was committed multiple files with each of the revisions, and maybe it was deleted. And you will not notice it if you don't run something like this, because the blob is still in the repository. What you save in Git, it stays in Git. And then finally, we have path all sizes and path deleted sizes. And basically, this is the different paths that you have with the sizes it's taking in repository. You may get like something that is changing quite a lot in the repository. Like, for example, a log file. Imagine you have a log file that you are updating every time a run happens. Then it will tell you that a specific file is not actually taking the size that usually that file takes. Like, for example, a log file taking a couple of kilobytes. But if you modify it and again and again and again, at the end, all of this space will be summed up, and maybe it's taking a couple of gigabytes. And finally, the renames is not something that you can take a lot of information from, but for example, you can find some patterns, like a log file that is being renamed every time you are committing because of an automation or something like that. If you see something that is a pattern that shouldn't be in a repository, just make sure you investigate it. And finally, I want to give you a couple of customer examples that we've seen during our engagements. So one customer basically was storing some emoji packs that was adding up to 1 gigabyte. And know what? It wasn't used at all. So these kind of scripts help them to understand what was happening on the repository and why they had that extra gigabyte happening in that repository. Another one, for example, had some language files that were actually being modified quite a lot, and they had a lot of entries because those files were really big. The packing processes were taking a lot and taking a lot of CPU from their machines. So splitting it or modifying the ways the languages were handled to the application just fixed the issue. Then another customer had some auto-generated files from local platforms that were just committing those files into the repository. And know what? The local platforms generate those files automatically. And this is actually a problem because each file cannot be delta and compared and compressed into the repository properly. And this is actually taking a lot of CPU and probably a lot of space, making the repository slow. Another one was just committing some testing databases into the repository, which at the end, the solution was just to move that testing database into a dependency and artifacts. And finally, the last one is just something that we've seen in a lot of customers, and it's just not using enough git ignore, adding libraries, binaries, build tools, these kind of things into the repository, which shouldn't be there. So now that you know some of the tools that you can run in your repository, it's time to run them. Remember to post the results that you are getting. We'll try to help you understand the data in the Slack channel, so just post it there. And you have also an issue in the repository where you see all the commands that you can run. And if you have any questions, just reach us and we'll try to help you there. Remember to obfuscate everything you put into the sensitive data because it's a public repository and we don't want you to leak anything. And for now, we'll just hit the timer and we'll start it. Just a quick reminder, when you are running these scripts, remember to post the results into this Slack channel so we can have a look to them with you and then make it a little bit more interactive. That's a good suggestion, so you get more insights from the running the scripts into your repos. if you can post your results on the activity too, so it's easier to read because on Slack it's a little bit hard to read on the threads.
Just a time check too. We've got about 10 minutes left on this activity. So keep working. Just letting you know we're about halfway through on this activity time. 5 more minutes.
Just 1 minute left and we're back. Great. So we're back. Hopefully you got some good insights from running those commands, and you now have more understanding of your repository and what is actually taking a lot of space there. Keep just posting the results that you have gotten on the issue number 2, and hopefully we can give you some insights if we analyze those. So now that we have analyzed those, what are the things that actually are preventing for these issues? First of all, git ignore and git attributes for git LFS are 2 things that are actually preventing our repositories for being so big, like 1 gigabyte size. Also, you can use git submodules to make sure that you just split your repository into different modules if you don't want them to sum it up in all one history. Additionally to that, you can use pull request reviews. And of course, pull request reviews itself will not save you time or will not save you some space in the repository. But at the end, with the reviews, you make sure that whatever you are adding to your repository should be there because you have another review for someone else. And sometimes it's just a mistake. Next one would be the GitHub Actions. So you can use GitHub Actions to check for LFS files or for files that should be in LFS just by adding one of the actions to your repository. One of them is built from our colleagues from Professional Services, and it's called LFS Warning, and it will give you hands-on whenever there is a file that shouldn't be in the repository but is committed to it. Then you have to make sure that your repository is less than 1 gigabyte. Otherwise, just analyze it and understand why it's over it and how you can fix that. And then you can also do a couple of things. One is restricting the object size. If you're using GitHub Enterprise Server, you can do that with pre-receive hooks. But if you are using just GitHub Enterprise Cloud, something that you can do is run it, put a hook locally so it prevents committing these files. But sometimes it's just that your repository is still big and you can't do much else. So we have something that you can do for you, and it's called grafting. And for that, I'm handing over to Sarah, who will tell about grafting.
Thanks, Javi. Like Javi said, another thing you can do to help reduce the size of your repository if it is already out of hand is grafting. As we covered in section 1, grafting is taking your current repository, moving it into a new repository without the baggage. And in this image, you can see that we have the old repository that's marked archive, and then we also have the new repository with the clean history. Now you see this connected history arrow on this image, but that connected history is actually on your local machine. It is not in the remote, which is on github.com, GitHub server, or wherever your remote server is for your Git repository. There's several steps to get to this phase though. Step 1 is to actually clean your current repository. Grafting your repository without cleaning it is like taking a dirty rug, putting it in your nice clean house, and that dirt actually still being there. You actually need to take that rug out, get the dust out of it, get it cleaned up before you put it in the new house. To do this, you'll want to do several things. One of those is to make sure that you have large files or binaries in the correct place. You need to remove any unneeded or unwanted files like emojis, log files, and those binaries that we just talked about. Also, any kind of automated files that aren't necessary to be in your repository need to be removed or their location changed for where the automation puts them. Any dependencies that could go into a dependency manager also need to be removed. An example of this would be the testing database that needs to be moved to a dependency manager or artifact manager so that it can be called on demand. Then removing any independent components or migrating them to Git submodules. And again, those aren't things that aren't necessary to be in your code. They just need to be available to run your application or run your testing. Then removing those binary files that should be ignored and adding them to your git ignore from the beginning, just like git LFS in your LFS files. You want to do this from the beginning so that the new repository has none of that history that was in the old repository, and it's not going to bloat the new repository from the beginning. Finally, review all of that automation we talked about that writes automatically. You may have already removed some of the stuff that was automatically put in your repository, but now you need to actually look at the automation that's writing it and make sure it's putting it in the correct location. Step 2 is going to be to create your new repository on GitHub or your Git remote repository location. You'll want to create a new repository to store the cleaned up, streamlined repository once you're done. Some suggestions here for naming for the old and the current repository are to rename the old repository that you're going to be archiving to something like repository X-2020, where the year specifies the year that the cleanup was done or that the repository was archived. You can also rename it in some way that is meaningful or important to your team and it's easy for them to find. As for the new repo, you could name it to the same name as the original repo that you're going to archive. This way it doesn't break any of your CI/CD anywhere that you've already got it configured for clones, pulls, and pushes. The only caveat here is that if you have specified versions or hashes, releases, hard-coded into your automation, those will break because when you move to the new repository, all of that information is no longer in the history. Now, again, you want to create this new repository as soon as possible, but you may not want to make the name fully until you're ready to switch over. You could mark it as new for now while you're doing some of the cleanup, and then when you're ready to do the switch over, rename it to the original repo name. Step 3 is going to be preparing for the grafting. You need to start from scratch to avoid leaving open work. To do this, there are several things to consider. One of those is communication with your team. This is paramount. You want to make sure that they know when the cutoff is for moving to the new repository, when the cutoff is for merging any existing work into the old repository, and that they know that that cutoff date is firm. The reason we say this is because you need to merge all work that is in progress in the old repository before actually moving the repository, because any open pull requests in the old repository are not going to be able to be moved to the new. Again, if it's not merged, it won't be moved. So make sure all those open pull requests and open work have been completed and merged into the head or the main branch that you're wanting to move prior to that change. And if for some reason you start in this process and find that it's way too complicated or you run into some major problems, we're always here to help. You're more than welcome to reach out to GitHub Professional Services for help. Okay, so you've done your cleanup. You're ready to move your old repository, transplant it into the new repo. This is the stuff that makes a lot of people nervous. We're actually going to delete your history from that repository. Now, to remove the history, we're going to do this all on your local machine. So you'll be able to see this happening on your local machine without actually pushing it up until you're ready and you're sure that you've done everything right. The first thing you're going to do is do a git status to make sure everything is there that you want and that needs to be there. There hasn't been anything that hasn't been merged, anything that hasn't been committed. Once you've got it in a state that you like, you're going to actually remove the .git folder. This folder holds all of the blobs and the history of all of the commits from the old repository. Yes, you heard me right. You're going to delete it. You're going to remove it. It's going to go bye-bye. Again, you're doing this locally. You're not going to commit this to your old repository. It is on your local machine at this point. Once you've removed the history, now you need to reinitialize this folder, this repository, as a Git repository with clean working history. To do that, you're going to do the git init command. It's going to replace that .git folder, but this time that .git folder is completely empty of history. Lastly, now that you've deleted the history, you want to create new history work log. You're going to set the origin for where the new repository is running as the git remote add in the git remote add origin command. This is going to point your newly cleaned repository with no history to the new repository location in the remote that you created. Now, all that history is gone. You have a clean repository that is now streamlined and everything's going where it needs to go, including your Git attributes, your Git ignores, your LFS, binaries are going where they need to go, log files are going where they need to go. You're ready to push it up to the new repository. However, first you need to write the beginning of the end. You'll need to run a git add to add all of the files in that file structure into the staging area for the first commit. Once you've added all the files, the first commit message needs to point to the old repository so that it does connect your histories in a way that you can find them if you need to go back for an audit or anything like that. Because remember, the history is still in your archive repository in your remote. Next, you're going to push that commit up to the remote. By doing this, you're writing the beginning of the end of the old repository and the beginning of the new repository. Now, optionally, as we stated earlier, you can connect the history of the old repo to the history of your new repo on your local machine. To do this, you would fetch the old repository back to your local machine again, and you would go do a git log just to make sure you have the one commit that you've previously had for the new repo. So that's the first commit of the new repo. Next, you're going to do a git replace to replace the hash of the new first commit from the new repo to the last commit of the old repository. What this will do is connect the histories of the two repositories on your local machine so that you have it if you need it for some reason. However, I would only suggest doing this if for some reason you do need that history. If you don't need it, it's always there in the archive repository on the remote. You don't necessarily have to have it on your local machine unless there is a specific business reason. Because not only is the old repository large and cumbersome, it's also probably several gigabytes that would be taking up storage on your local machine. Again, you can connect it locally if there's a business reason, but that is a decision that would have to be made on a personal or a business basis. So now we're going to verify that you can work in the grafted repo by checking that your commits are going to the correct remote repo. To do this, we're going to simply do a test commit with the test file. You would commit it and check that you can navigate to that one commit or that history that is only showing the one. You should then push the remote repository and push it to the remote repository and validate on github.com or GitHub server that it is going to the new repo and not the old. Again, this is just validating that your connections are correct. Here's an example of the grafted Linux kernel when we did the test grafting on our local machines. You can see the log after we did the grafting on our local that this is all the old history. It does not have that initial first commit from where we did the cleanup and the grafting. However, when we look at our example repo in github.com, you can only see the first commit from that new repository and the second commit, which is the test commit. Now, fun fact about Linux kernel, it has been grafted several times over the years and has a log, and there is a log of those graftings at archive.com. We've given you a few tools. You've done some analysis on your repositories. You know what's in the repositories that you may want to move or may want to clean up. In activity 3, we want you to actually start doing some of that, doing some of the cleanup and possibly doing a small grafting. We're going to give you 20 minutes. We know 20 minutes isn't going to get you very far, but you can probably at least get a start on it and execute some of the commands and see some of the cleanup activities in action. Once you've completed some of the cleanup, we want you to go back and run those analysis tools again and see if you find any improvements in your repos that you're practicing on. Once you're done, we'll come back. If we have time, we can discuss some of the results. We will have a period of time at the end for Q&A. If you have questions, though, please feel free to reach out to us in Slack or in the issue. And we're going to give you 20 minutes with that fun elevator music some more, starting now. Let us know if you need help.
Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Who says to break the game, baby? I'm number one. Know your body type. Know your body type. Backfoot, 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 backfoot. Know your body type. Know your body type. Backfoot, 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 backfoot. Know your body type. Know your body type. Backfoot, 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 backfoot. Know your body type. Know your body type. Backfoot, 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 backfoot. Know your body type. Know your body type. Backfoot, 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 backfoot. Know your body type. Know your body type.
All right, folks. To use the time a little bit, I would like you, if you're interested, I would like to draw your attention towards our second issue about the activity 2, where Todd O'Connor posted quite interesting results there that I think are generally, yeah, that are just that apply to many repositories that we have seen at GitHub Professional Services over the years. So Sarah, yeah, let's take a Git sizer output first. So the first thing that we see here is there is a 200 megabyte file in the repository. That is always something to look for. I mean, 200 megabyte is a pretty big file. It's unlikely that is source code because you would need to write a lot into a file, and therefore it is usually a good candidate for Git LFS. In general, as a rule of thumb, I would say every file that is larger than like 500 kilobyte or maybe a megabyte should really be considered for Git LFS, because these files are usually no source code files, as source code files usually don't get so big. And the problem is that these very large files, they sometimes don't compress well, and so they basically make your repository really big, so they increase the size that you need to, or increase the amount of data that you need to clone or fetch when you get the repository. Yeah, so bottom line is watch out for the maximum size blob when you look at your Git sizer output. Let's move on. So yeah, let's stop here really quick. There's another repository. As you can you go up a little bit? That is another repository, but as you can see here, it's the very same thing. It's a 500 megabyte file in here, and that is really the only major concern. I would say maybe 90% of all the repositories that we see have the issue. There are just a few very large files in there, and they are responsible for most of the size of the repository. And usually these large files, sometimes these large files are not even used anymore. They just have been committed years ago, and now they're just carried around. And that is actually what you can fix with the grafting trick that Sarah just explained. So let's move on to yeah, there's some Git LFS extensions output. So let's discuss this really quick, what that actually means. So here we see there are, so the first line means all the files. So, or okay, if you run Git LFS git find LFS extensions, it looks for all the files in your head revision that are larger than 500 kilobyte. You can define the threshold with a parameter here, but the default value is 500 kilobyte. So apparently the repository that Todd ran this against has in total 11,000 files in the head revision, and 500 of them, so 4%, are larger than 500 kilobytes. So 500 of them are potential candidates for Git LFS. And the total size of all the files is almost more than 3 gigabyte. And the biggest file is 149 megabyte. So that is the general overview. Now let's look at the individual file types. And the first one here is DN files. So I don't know what DN files are, but 100% of these files in this repository are actually bigger than the threshold. So there are, let me clear that up again. There are 94 DN files in the repository, and 94 of them are bigger. So this means if you see like 100% of these files are larger than 500 kilobyte, that is a very strong indication that this is a good Git LFS candidate. The reason we're doing that here is that if you have, let's say, for instance, in C++ development header files. You might have a big project with maybe 10,000 header files. And it might be that whatever 2 or 3 header files are really large for whatever reason. And this is, in that case, it wouldn't be a good idea to move these header files to GitLFS, first, because that's really source code. And second, GitLFS works on file extensions. So if you move header files to GitLFS, then that means all your 10,000 header files would be moved to LFS, and not just the 1 or 2 that are really large. So that's why you want to always look at the percentage of files, or when you want to always look at a certain file type and then check what percentage of that file type is actually big. So again, the end files, 100% of these files are considered big. It's also binary, so that is a prime candidate for GitLFS. And the same is true for other files here, like, for instance, DLL, lib, SO files. These are all compiled library files, and it's probably a good idea to put them in some kind of dependency management system, depending on what language or what programming language is used here. A popular, so if you have no native dependency management system, like C++ doesn't really have one, then you could also upload these files to an artifact storage like Artifactory. So this is an option, or alternatively, you could also store them in GitLFS if you want to. And you can see here, a good percentage of these library files are actually bigger than our given threshold. So just to go over this example here, DLL files, 72% are larger, and the largest DLL file is actually 42 megabyte, which is a clear indication for good LFS. Yeah, that is a good LFS candidate. So yeah, let's move on a little bit. So here, maybe stop for 1 second there. So this tool will also show text files, as you can see here. And here we have the header file that I just talked about. So apparently this project has 3,819 header files, and 12 of them are actually larger than 500 kilobyte. And that means 0%, like point something percent of the files are considered large. So that's no good candidate for GitLFS. And actually all these files, since they are text files should always give you a pause. I mean, there are some cases where you want to put text files into LFS, but it's really, really seldom. All right, then let's move on. So here we got some output. Let's move further for the Git filter repo output that Todd shared. Is very interesting. Yeah, let's look at this one. So there is this file extension all sizes. That basically means the analysis tool looks at all your PNG files and at all your DN files. So it looks at all your file extensions and tells you how much space they take up. And here in Todd's repository, we can see PNG files take up most of the space because they are on the first line in this result. So this is a very big number. I don't know, that's gigabytes of data. So the repository itself is not that big because Git is very smart in combining these files and compressing them very efficiently. But still, this tells us PNG files are the biggest contributor to the size of this repository. And that's, again, is a good candidate for GitLFS, or that makes them a good candidate for LFS. These extensions, all sizes, comes in 2 flavors, deleted and all. So with all, we basically see extensions that are still present. Deleted are extensions that are not even available in a header version anymore. So you carry them around, although they are not used for years. As you can see here, they have been deleted. Some of them here in 2016, they have been deleted in 2016. Yeah. So again, this is a good. The best way to clean that up is really to use what Sarah just explained with the grafting. And last but not least, here you see the path our sizes output. And here we can see, for instance, there's a component path 1 that takes up a lot of space. This can happen if, for instance, if you have a Ruby project, or if you have files that are automatically generated and maybe updated with every commit or so, then these files can add up. So the size of them can add up, and this contributes then to a large repository size. So the learning here is basically, if you have files in your repository that are auto-generated, then you might want to consider to auto-generate them on build instead of committing these auto-generated files to your repository, because, as I said, these are usually contributors to large repositories. Okay, and now we are almost up with the break, and that's why I will stop. So please add your own results to these issues, and then we can review them offline. Thank you.
Thank you, Lars. Yeah, as Lars said, we've got about a minute left, so we'll let you continue working on that activity 3, see where you can get in that 20 minutes that is nowhere near long enough. All right. So I know, like I said, the 20 minutes is not really a long time for you to be able to get real far down into the cleanup and the grafting of your repository, but hopefully it gives you a quick insight on how small changes can make a big difference. And with that, I'm going to go ahead and turn it over to Javi. He's going to go through some of the things that we realized with the Linux kernel.
Yeah, so before we start with the analysis that we did with the Linux kernel, I would like to just do a quick refresher of what the grafting at the end did. And basically, we created a new repo. We have still the old repo, and we're connecting the histories. But at the end, we're just taking whatever is in the head of that repo to the new one. So basically, your repo analysis will look as it looks in the head of that specific repo. That's why we say, first, you need to clean up your repo. Otherwise, you will carry over everything that you have on that repo to the new one. And that's why all the cleaning up makes sense. So we did that on the Linux kernel. We didn't really clean up anything. We just ran the grafting to see how it looks like. And it's pretty interesting because actually, as we told before, the Linux kernel is a really good repository in terms of what kind of content it has in it. And that's why the grafting is really working a lot well in this repository. And you can see that the processing blobs has decreased by 97%. And this is because most of the blobs that we have there is because of the history, not because of the blobs are too big or something like that. If that number wouldn't look as good in terms of the amount of data that we are carrying over, then probably we should clean up a little bit more. As you can see, happens the same with the trees, 99% of reduction. And of course, for commits and the matching commits trees, it makes sense that it's 100% reduced because at the end, we're just cleaning up the history, right? And keep in mind that we run this with the repository and the grafted history, not the full history. So. if we see also the statistics on the amounts in size, we see again a big reduce in there. So we see the trees has been reduced by almost 100%. It's 99 something. Same for the blob size, it's 98% of reduction. And the commit size, again, we are not carrying over all the messages, but we're just connecting them from the two repos. So at the end, you have all the good things from both worlds. You have a fast repo that is easy to use and easy to maintain, while you also have the history from the previous repo. And if we check, one of the main variables is the cloning time. Sorry, this is the time it took to run the git sizer. So first time it was 3 minutes, and now with the grafted repo, it was 0.3 seconds. This is a big improvement. And as you can see, it actually takes way less time to process it. For the three next scripts that we run, the git find LFS extensions, git find many deers, and the unwanted deers, the three scripts, we didn't find any kind of relevant improvement. And this is because, as we told, the Linux kernel is already a good maintained code, and they don't have something that shouldn't be in the repo. And because of that, all of those that are meant to find those statistics that are really bad for your repo, they are not really showing any kind of improvement because we have improved the history. And finally, for the Git filter repo analyze, what we've done is checking again for the blobs commits and some of the blob sizes. And as you see, it's again the same kind of percentage in reduction. Again, it makes sense, right? Because we have just taken over the whole history. And finally, for the script runtime, we see this one took around 7 seconds, or 8 seconds, while the first time we run it, it took 18 minutes. So it's actually a big improvement on how you can analyze the new repo. So we want you to take some takeaways from running all these scripts into your repos, and also the grafting operation that you can run to improve the performance of the repo. So first of all, there's a clear improvement in the operations speed with Git interactions. And this is just for the analysis tools, but you can think the same for Git clone, Git fetch, and any other operations that you run every day. They will be faster because they are acting against a history that is smaller. Also, just a quick comparison on how much speed it took on the clone. The Linux kernel took from 11 minutes to 31 seconds. We actually have some people in the chat commenting that actually it took around 30 minutes to clone the repo. So imagine how much time are you saving for your developers just by reducing the size of the history. Of course, again, if you don't clean up your repo, you will carry it over. And yes, at the beginning it will be better, but with the time it will be worse and worse, and you will have the same problem and you will have to do grafting again. So first of all, clean it up and then move everything over to the new grafted repo and start working there. And since you have the connected histories, you will be able to still do all the good things that Git offers, like blaming someone when you see a line that it's a little bit catchy. You also have a faster CI at the end. You know, productivity in the CI is better, and if you are paying especially for a cloud in the CI/CD space, this will probably impact a lot your billing. Because your CI/CD tools will take less to clone your repo and run the continuous integration processes. You will have a developer experience improved just because, you know, all this time that you're saving. Of course, less coffee, but still something good to improve. And finally, yeah, your server resources, we told that actually it's consuming a lot of CPU just by having these operations with big repositories. You'll save that, and maybe you can even save some bucks just by reducing the size of the machine if you're hosting it yourself. And yes, basically, this is giving you a scalable process for the future generations of your code. So whenever your history is piling it up, it's getting harder and you can't really maintain it, just graft it, clean it up, make sure you keep going with your history. And I think with that, we have arrived to the end of the presentation. We'll love to open some space for Q&A. So feel free to jump in and give us some questions. And thanks again for coming.
I'm not sure. of course, we'll take questions in Slack and then also in the issues, and we can try to cover some of those too. Lars, if you or James or if y'all saw some very good examples, we can always post those or show those on the screen as well.
Yeah, there's a question right away from Novalis, and the question is, given that we now have partial clones, grafting seems less useful, right? Well, the thing is, so I want to distinguish between two things. So we have GitHub Enterprise Server, that's our on-premise product, and there is github.com, which you interact with right now if you look at our repository. And github.com has a lot of servers. We have an amazing infrastructure that can pretty much handle any load. So very huge repositories on github.com just work. But on GitHub Enterprise Server, you have your own infrastructure. And this own infrastructure is oftentimes limited in the sense that you cannot, you don't automatically scale. And for these for repositories on your own infrastructure, large repositories that are active can become a problem. And therefore the grafting method helps there a lot, because if you run partial clones only change the amount of data that is downloaded from the server to your local machine, but the server still needs to work with the entire repository. So yeah, that's why I would say partial clones don't help too much here if you're talking about GitHub Enterprise Server, because partial clones only help the client if a repository becomes too big. Does this answer your question, Novalis? Maybe you could respond in chat, and just looking if there are any other questions.
I see some people typing, so I don't know if it's a question coming in. So Matt asks, is there any plan for GitHub to analyze repos and provide suggestions for these types of optimizations?
That's a very good question. And actually, we already do that. Our so if you're an enterprise customer, you can there's like we call it a health check that you can ask our support engineers to do, and then they will analyze your GitHub Enterprise appliance. And in that task, usually they also look at larger repositories. Yeah, so we already do this, but there's no public way to do it right now, because these optimizations are usually, first, they are opinionated, and second, in order to make a good assessment, you need context. So by just looking at your repository, you can only discover the most obvious cases. Yeah. So bottom line is, if you're interested and if you want your repository analyzed, then please reach out to us, and then we can schedule a professional services session, and then we can look at the repository together and guide you through optimizations.
And also to add to the answer, the best optimization is to have gates to prevent that to happen. So at the end, if you set up your CI/CD tools, even with actions or whatever CI/CD pipeline that you have, you may be able to prevent these kind of things to happen. And the most common one is just committing things that are not meant to be in the repository, but in LFS. So the action that we showed before from Action Desk LFS warning may help you to achieve that. And of course, you can build your own with the APIs. So it helps you a little bit to prevent those kind of issues to go to your repo and stay there for the future.
All right. Looks like we may have a couple more coming in. thank you for your feedback too on the presentation of this workshop. We're always looking to improve things and make them better and make them more personable. So any feedback is greatly appreciated. Even if it's that I didn't dance during the hold music.
Yeah, it was easy when there was some music. Okay, so there seems to be a question. So if my analysis finds that there are large groups of files that I would like to separate into a different repo, what is the best way to clean up for the original repo so that the history or blobs for those things are not left hanging around? I can take that one. So at the end, what you're taking out to the new repo is just whatever is in the head that you are cloning or you are getting, right? Because you are removing the Git history. So I would say the best thing to clean it up is just clean your head revision, put whatever needs to be in your LFS storage, and whatever needs to be, go to the dependency management system, or just remove whatever is not used. And keep in mind that you will just take out all the things that you had in the history from before. Like, for example, one time you committed a big file, but now it's removed and you don't have it in the head history. That's fine. You will not take that over. So that will not count on your new grafted repo. So at the end, as much as you can clean your head revision, that's what you will take out to the new repository that you're creating. Hopefully that answers the question. If you have anything to add, Lars or Sarah, feel free to jump in.
Yeah, maybe one addition is, so if you do these kind of operations, I highly recommend to check out a tool. It's called that we've referenced earlier too, Git repo filter, filter repo, which you can use to do all these kinds of things like slicing and dicing repositories to bring them into the shape you want. So that is I will post the link again to the Slack channel.
Thank you.
And also for the ones who had the question on where they can find all this information in the repo, there is the key for the presentation, and you also have a PDF if you want to download it.
Yeah, and all of the commands that we ran on the Linux kernel and showed examples of today are in the README in that repository as well. And then also the issues have just basically a copy of those commands that are in the README. So if you have the README from the repository, you have all the commands that we ran today. All right.
You still have 10 minutes, around 10 minutes, or? I think so. So if you still have some questions, feel free to post them.
And as the slide says, we will have the Slack channel open until the 16th. So if you do have questions that come up over the next 5 days when you're trying this out, do feel free to jump in there and we can maybe give you a few answers or clarify some things if you have questions. So that will be open and available for the next 5 days.
So a new question, just to know for GitHub Enterprise Server, this step to push to the new repo, that new repo should already be created on GitHub Enterprise Server. Yes, yes, it should be created, because otherwise you won't be able to push. And also keep in mind that whatever other copy you have of the previous repo, you should just clone the new repo from scratch, because if you do a remove remote and then change the remote to the new repo, you will be pushing the whole history from the old repo, and that would bring like all the problems that you have in the previous repo to the new one. So that's also an important note to give to all the teams that work in the grafted repos, to use and clone the new one and start working there, and do maybe the grafting operation afterwards if they want to use the history.
And maybe one addition to that, so there is on GitHub Enterprise, you can use pre-receive hooks to check all the commits that are pushed to the GitHub Enterprise appliance. And one of these pre-receive hooks is that I just posted in the Slack channel. Its name is reject commits. So with this pre-receive hook, you can ensure that certain commits are never pushed again. And this way you can basically ensure that someone does not accidentally push commits from the old repository to the new one, because that, as Javier said, would increase the size of the new repository again. So this is a very useful pre-receive hook to install if you do this kind of operation on your GitHub Enterprise appliance.
Thanks for the point, Lars. I actually forgot that.
Yeah, and pre-receive hooks are only available for use on GitHub Enterprise Server at this time. They're not available on GitHub Enterprise Cloud or github.com.
Yeah, something you can do as well is make sure, so communication again is really important for the team, but if you set up like a setup script that basically does the grafting for you, and you put in your instructions to, hey, first clone the repo and then run the grafting, maybe you can add there some scripts to add also a pre-commit hook, so you also avoid doing something like that.
Yeah, defining that in the README of the repository helps with the communication to your teams. Any other questions? If not, we could give you a little time back. Someone's typing. Let's see if it's a question. Oh, yep. Will GitHub Universe workshops repositories be alive forever, or is there a plan to shut them down? I honestly don't know the answer to this question right now. Lars or Javi, do you?
No, me neither.
I think they're there in perpetuity. They just might move to an archive state where they can't have changes made to them.
I think previous years are not there, so it's very likely that at some point we archive it.
Well, I think the previous years they're going to actually migrate into this new org. So to get them all in one place, I think I remember reading that. We can check on that definitely, Ivan, and get back with
an answer.
Yeah, get an answer to that. We'll post it in the Slack when we have an answer. All right. Well, we really appreciate you all joining us today. We hope that this was very helpful and insightful, and we hope that it is definitely something that you can take back to your own teams and repositories. There will be, I believe the recording will be sent out after the session today. I believe that's right, Faith? It'll be emailed out. Sorry,
Yes.
I know.
Yep, that's right.
So yeah, we'll get the recording, and of course you've got access to the repository that has the keynote and the PDF of the slides along with all the steps we did. But if you do have questions, let us know. And otherwise, thank you again for joining us today.
Thanks a lot for joining us in this workshop, and we hope you enjoyed it. So we see you in the next universe.
And beyond.
And beyond.
Thank you all.